for the good old days. Wasn't that a beautiful Model T? And then again, wasn't that a beautiful Corvette? It all depends on your point of view. One thing is for sure, the old cars were easy to repair. Well, things have changed. Added conveniences and government regulations, anti-skid and airbags, four-wheel drive and four-wheel steering, even environmental temperature control. The method? Electronics, computers, the little black box.
The Corporate Training Department of Standard Motor Products presents this video training program as part of our continuing effort to keep you up to date on how to repair today's cars and remain profitable. This standard electronic engine controls training module covers the Ford electronic engine control system. In order to confidently and profitably repair these systems, the mechanic must have certain hand tools and test equipment. Also, he should have a working knowledge of the basics of electronic engine control systems and an understanding of the Ford EEC system. And most important, he should be familiar with electrical and electronics diagnostics procedures.
Let's briefly review some general aspects of Ford electronic engine control. Then we will diagnose some on-vehicle problems using the Ford onboard system and also some simple test equipment. Ready?
Ford has utilized one basic overall system for electronic engine control. Most people refer to this as the EEC system, introduced by Ford in 1978. Over a period of time, there have been numerous versions. The EEC-1 system controlled ignition, timing, and the emission system. It was used on the 5-liter Lincoln Versailles. This system did not control the fuel system. In 1979, Ford introduced EEC-2. It controlled the ignition timing, the emission system, and the fuel system. It regulated the air-fuel ratio using an information feedback loop having an oxygen sensor. It controlled a variable Venturi carburetor. EEC-3 was introduced in 1980. Though it was similar to the EEC-2, Ford changed to a 7200 VV carburetor. The same EEC-3 system was again expanded in 1981 to include electronic fuel injection. The early fuel injection systems were actually throttle body assemblies utilizing one or two electronic fuel injectors. In 1984, EEC version number 4 was utilized on the 5-liter engines. EEC-4 was actually introduced in late 1983 on Escorts and Lynx vehicles equipped with the 1.6-liter electronic fuel-injected engines. The EEC-4 system offered expanded capabilities in diagnostics and the level of engine control over version 3. It continues to be Ford's main offering. To eliminate any confusion during this program, Ford's MCU, Microprocessor Control Unit, should not be confused with the EEC systems. MCU, introduced in 1980 by Ford on California vehicles, has been used right through 1985 on various engine chassis packages. But the system does not control or interact with the ignition system in any way. It is merely a fuel control system. From the first EEC-1 system in 1978 until the EEC-4 system of the late 1980s, Ford has added, with each variation, more enhanced capabilities to control the drivability functions of the automobile and still meet emission and mileage standards. The primary influence on the ECA is supplied by sensor input information. The late-model EEC-4 systems incorporate input information supplied from TP, or Throttle Position Sensor, MAP, Manifold Absolute Pressure, or BP, Barometric Pressure Sensor, and ACT, or Air Charge Temperature, MAF, Mass Airflow Sensor, EGR, EGO, or HEGO, Exhaust Gas Oxygen Sensor, or Heated Exhaust Gas Oxygen Sensor, ECT, Engine Coolant Sensor, PIP, Profile Ignition Pickup, a signal from the engine's distributor for RPM and cylinder position, a series of miscellaneous switches, including transmission switch, power steering switch, AC switch, etc. and some vehicles use a knock sensor. The ECA, or Engine Control Assembly, utilizes the various sensor inputs, processes the information along with pre-programmed operating instruction memory and calibration memory from a calibrator, makes a decision, and responds to various controlling devices in either the ignition system, fuel system, or emission system. Since this program deals primarily with the EEC system as a function of ignition or timing control, the output of the engine control computer will be to either a DuraSpark ignition module or the TFI, Thick Film Integrated Ignition Module. Beginning around 1983, the thick film ignition system was introduced on the 1.6 and 2.3 liter engines and has since been used across all engine configurations since 1988. The late thick film ignition assembly works with a Hall effect sensor or Hall effect pickup in the distributor. Earlier versions use magnetic pickup assemblies. A very common complaint on early thick film systems happened when the plastic housing of the ignition module itself separated from its base plate. This caused an intermittent no-start condition. Let's take a closer look at the EEC-4 electronic engine control system. One benefit or feature of an EEC-4 system over earlier systems is its adaptive strategy and keep-alive memory. Adaptive strategy allows the computer to make modifications for wear and age of the engine and other components. It has the ability to learn. This adaptive strategy also functions with another modification called FMEM, Failure Mode Effects Management. Whenever the engine is in this mode, a code 98 will display. The CAM, Keep Alive Memory feature, allows the computer to retain diagnostic code information when the vehicle is shut off. Another feature of the EEC-4 system was introduced in 1988 models: the utilization of the check engine light on the dashboard to display diagnostic codes. A closer look at Ford's electronic ignition system shows that of all the sensor inputs to the computer, the ECA assembly uses mainly the ECT, or engine coolant temperature sensor, TP, throttle position sensor, PIP, profile ignition pickup, the EVP, or EGR valve position sensor, ACT, or air charge temperature sensor, and MAP, or manifold absolute pressure inputs, to supply information that the computer uses to control timing. You must keep in mind that the main reason for controlling sparks so accurately is to derive maximum engine power, or drivability, and still meet the emission control and fuel mileage standard mandated by the federal government. Let's study the circuits and components of the Ford system. The thick film ignition module is similar to the ignition module that you've seen for years on General Motors vehicles. It is a miniaturized electronic circuit with a switching transistor. It is mounted outside of the distributor case, either on the distributor body or in the cowl. The system uses no centrifugal or vacuum advance mechanisms. All spark control timing is performed in conjunction with the thick film module and the ECA assembly. The PIP, or Profile Ignition Pickup Assembly, is a Hall effect unit. The Hall effect signal to the TFI module is conditioned and sent as a PIP signal to the ECA unit. The ECA consults pre-programmed memory and additional sensor inputs, makes a decision, and responds with a spark output signal back to the TFI module. The TFI module then controls the primary power to the ignition coil. This primary power control determines the discharge cycle of the ignition coil and, consequently, timing. One feature of this system is that if the ECA assembly becomes damaged electronically, or if one of the primary timing control sensor inputs to the unit malfunctions, the TFI module will allow the ignition system to operate in a fixed or base timing mode, as long as the PIP signal is still being received by the TFI unit. One last piece of information we should introduce prior to diagnosing some on-vehicle problems is to mention that in 1989, Ford introduced a direct ignition system. Direct ignition is utilized on the twin spark plug 4-cylinder Ranger engine, also on the 3-liter dual overhead cam SHO Taurus engine, and on the supercharged 3.8-liter Thunderbird and Cougar models. The system utilizes a coil pack containing individual coils for each of 2 spark plugs. One spark plug fires on the compression stroke and utilizes the majority of the spark energy from the ignition coil. The opposing cylinder on the exhaust stroke is simultaneously fired with the waste spark from the same coil. In the place of the typical distributor, a camshaft position sensor is utilized that contains a Hall effect sensor. It operates similar to a profile ignition pickup assembly that you are familiar with. The cam sensor's output, in conjunction with the ignition control module, operates with the EC4 computer system the way it always has.
That's it. We've covered the basic components of the Ford system. Now, to repair some common problems. Hands-on experience may be the best teacher, but through the use of video, we can simulate almost everything except your hands actually touching the components. With some simple hand tools and a few pieces of test equipment, any problem can be solved. Let's take a closer look.
The owner of this Taurus has been complaining about a loss of power. The first problem is deciding whether the condition is fuel-related or ignition-related. Obviously, it could be any number of things, so you need to follow a logical approach to troubleshooting. The first step to a successful repair is to derive some general information, particularly the VIN code and the exact details of the complaint. Always ask the customer the questions necessary to determine exactly what the complaints are and when they occur. Remember, you cannot diagnose a problem that does not exist. Next, do a complete visual inspection, checking the spark plug wires, the air filter, battery terminals and voltage, the output of the charging system, the coolant and antifreeze level. Check the operation of the engine's coolant fan and always double-check sensor lead wires and connecting clips. With the necessary information in hand and the visual inspection complete, you need to isolate the system which is causing the problem. This can be accomplished by using either engine analyzers or handheld test equipment. If you are working on a 1988 or newer model, deriving diagnostic codes can be done utilizing the onboard dash indicator light. Since the complaint is intermittent, lack of power, or as the owner describes it, some type of a flat spot or a hesitation when he steps on the throttle, your first concern is to determine whether the problem is fuel-related or ignition-related. Any number of steps could be taken next. You could follow a symptomatic troubleshooting chart, or you could use the Ford H manual or any comparable service manual. But you should follow a logical sequence of testing. Ford has a vast array of tests available. One is referred to as a key-on, engine-off self-test. Another one is called a computed timing check. Another one is called an engine running self-test, and even a continuous self-test. You also have a choice of test equipment to check the EC4 system. We will illustrate the use of a scan tool, an analog voltmeter, and the dash light to derive trouble codes. The first step in properly diagnosing this vehicle is to do the visual inspection we have already completed. The second step is the actual vehicle preparation before installing test equipment. Ford recommends setting the parking brake, placing the transmission lever in park. Turn off all the electrical loads, and always make sure that the doors are kept closed. Next, run the engine until it has reached operating temperature. Turn off the engine. It is a simple matter to utilize the check engine light. After locating the diagnostic self-test connector in the engine compartment, connect a jumper wire between the single self-test input lead and the 6-pin self-test connector as shown. Turn on the ignition key engine off, and record any on-demand or functional test codes that appear. The on-demand codes indicate that there is a malfunction at the time you are self-testing the EEC system. These are referred to as hard fault codes. If you are using an analog voltmeter to test this system, it is a simple matter to connect the voltmeter. Attach its positive lead to the battery. Hook its negative lead to the self-test output terminal. Install a jumper wire from the single-pin self-test connector to pin 2 of the 6-pin self-test connector. Set the analog voltmeter to the DC voltage range of approximately 15 volts. Turn on the ignition key and count the pulses of the needle. Remember, all fault codes are 2-digit numbers, like an 86. The analog voltmeter, the dashboard indicator light, or the scan tool will all give the same results, and all will read out the hard fault codes held in memory or detected during the functional test. We are receiving a code 11, which is an indication of a pass. No fault codes detected at this time. After a few seconds, we will receive a code 10 on the scan tool, or an individual pulse on the analog voltmeter. This is called a separator code. The computer will now check for continuous memory codes. It will search its memory bank for any codes that have been held in memory. These codes would be the result of a prior fault in the system, not necessarily present at this time. A code 18. You should always repair the on-demand codes first and receive a pass code 11 before doing any other testing or any other repair work on the vehicle, even if a continuous memory code exists. Since we know we have a problem and we do not have any on-demand codes, the next test will be a timing check. This will verify that the ECA assembly is properly advancing the ignition timing. Ford states if the base timing is 10 degrees before top dead center, self-test timing should be equal to 10 degrees fixed timing plus 20 degrees computer advance for a 30-degree total. For the exact base timing specifications, you should check the Vehicle Emissions Control Identification decal that's located in the engine compartment. Turn the key off. Wait approximately 10 seconds. Restart the engine. Check the timing while the vehicle is in self-test. To check timing, pull the computed timing plug. Timing is as specified. Reinstall the computed timing plug. Let's not give up. We have not yet located the source of the problem. Next, we will do an engine running self-test. The first step in doing an engine running self-test is to deactivate self-test. Disconnect the jumper wire from the self-test input terminal or the individual lead from the scan tool connector. Turn the engine off. Wait 10 or 15 seconds and restart the engine. Reactivate self-test by installing the jumper wire or plugging the individual lead into the scan tool plug. The scan tool or the voltmeter will next give an indication of an engine ID code, which allows you to verify if the proper computer or processor is installed and the self-test has been entered. Engine ID code is equal to 1/2 the number of the engine cylinders. For example, 4 pulses on the voltmeter would be an 8-cylinder, or 2 pulses would be a 4-cylinder. The scan tool will indicate 20, 30, or 40. We are working on an electronic fuel-injected 3.8-liter 6-cylinder. Immediately after we receive the ID codes, we should depress the brake pedal. This will allow the engine control computer to check the brake switch for functioning. Next, turn the steering wheel approximately 3/4 to a 1/2 turn and release it. This will check the power steering switch. Next, quickly stab the throttle for a wide-open throttle position. Next, you will receive engine running diagnostic codes or hard faults if there's a problem detected during the engine running self-test. We are receiving a code 11, indicating that the vehicle has passed and that there are no codes held in memory. The next test we must perform is called a continuous self-test. This is where we will locate the intermittent problem. Ford refers to this as a wiggle test. You should not perform this test until you have gone through all of the previous test sequences. To perform a continuous running self-test is quite simple. If you remember, we had logged a code 18 while performing the continuous self-test. The first step of the wiggle test is to erase any of the continuous memory codes in the system. Perform a key on, engine off self-test, and then exit the self-test while it is in progress. This will clear all continuous memory codes. The wiggle test can be performed as a simple key on, engine off test or as a key on, engine running test at your option. If it is performed as an engine running test, start the vehicle and activate the self-test. Approximately 2 minutes after the passcode 11 has been displayed for on-demand codes, the system will enter continuous monitor mode until you deactivate the system by turning off the engine. Carefully go through each wiring harness, sensor, and solenoid assembly, tapping, wiggling, twisting wires, etc., until you have initiated a code. We have a continuous self-test code 18 again. The service manual directs us to pinpoint test N, Ignition Diagnostic Monitor, IDM. During this test, we are going to check out the ignition module, the ignition coil, the secondary circuit, the distributor, and the PIP sensor. We are looking for problems in the ignition harness, ground, spout, PIP, or IDM itself. If you recall the ignition circuit, we illustrated where the PIP sensor sends a signal to the ignition module and then to the ECA. The ECA assembly returns a spout signal back to the switching transistor in the TFI assembly to control the primary current flow through the ignition coil. We have checked timing advance and it functioned during the test period, but the fact that we have a continuous memory code 18 indicates that at some time in the past the system might have reverted to base timing. This could be the cause of the intermittent problem. With the system in continuous self-test and the engine running, move the wires from the TFI assembly. A code 18. Shut off the engine and disconnect the TFI module lead wire harness and inspect the connections. There is the problem. Someone has left the weather pack seal off the module assembly. It appears that a replacement unit has been installed in the past, and with the weather pack seal left off, moisture has caused corrosion on the pin connectors. It will be necessary to thoroughly clean and dry out the TFI module and the harness assembly. Install a new weather pack seal. Re-enter self-test and disconnect the jumper wire from the self-test connector to erase any diagnostic codes. Turn the ignition key off. Wait approximately 10 seconds and reinitiate self-test. Key on, engine off. A passcode 11. A separator pulse, then another passcode 11. Now, start the engine and repeat the wiggle test and watch for a diagnostic code.
This concludes working on Ford electronic engine control. As you've seen, it's easy to troubleshoot and repair the system. I would like to take this opportunity on behalf of Standard Motor Products and its training department to thank you for purchasing this program, and we hope you will consider us for your future replacement parts needs.